Welcome to an overview of our work, Sparse PointPillars, maintaining and exploiting input sparsity to improve runtime on embedded systems. Today, all kinds of depth sensors are readily available for mobile robot platforms, which provide more insight into the world around our robot than from cameras alone. But this begs the question, how do we effectively process these point clouds on our robot? The autonomous vehicle literature has been exploring this question for a while in order to process the point clouds generated from LiDAR, making the related literature an excellent resource. One of the most popular point cloud object detectors is PointPillars, a bird's eye view style detector that operates by taking in a point cloud, pillarizing the scene into a regular grid, and vectorizing the non-empty pillars, producing a pseudo-image. This is a visualization of a real pseudo-image with non-zero pillars shown in white and zero pillars shown in black for visualization. This pseudo-image is processed by a feature pyramid ConvNet backbone and then a single-stage detector, an off-the-shelf bounding box head used to regress 3D bounding boxes. PointPillars is popular because not only does it produce good detection quality, it's fast relative to its peers, boasting 60 to 100 Hz performance depending on the configuration. But these results are on high-end desktop GPUs. As roboticists, we want the runtime and performance of PointPillars, but run on embedded ML accelerators or robot CPUs. To do this, we designed a new pipeline based on PointPillars that exploits natural representational sparsity that we call Sparse PointPillars. Our key insight is that pillar inputs are fundamentally sparse, but this sparsity is ignored by PointPillars. In practice, during pillarization, only about 3% of the pillars have any points in them at all, and PointPillars even store these vectors in a sparse coordinate-style matrix. However, PointPillars chooses to convert this sparse matrix into a full dense matrix to be processed by the dense convolutional backbone, thereby enjoying no performance benefits due to this sparse structure. In Sparse PointPillars, we preserve the sparse COO representation and feed it into our sparse backbone, which leverages and preserves this sparse structure to do fewer computations. This is a depiction of the two backbones, with PointPillars on the left and Sparse PointPillars on the right. The overall feature pyramid structure remains the same, but Sparse PointPillars uses carefully placed sparse and sub-manifold convolutions, or sub-M-convs, to maintain and exploit input sparsity. To illustrate the differences between standard or sparse convs and sub-M-convs, consider this example. In each picture, non-zero entries are shown in white and zero entries are shown in black. Sparse convolutions exploit the representational sparsity by skipping zero entries, but they are mathematically equivalent to standard convolutions, resulting in smearing along edges due to convolutions centered on zero entries providing non-zero results. Sub-M-convs are not mathematically equivalent. They only run centered on existing non-zero entries, avoiding smearing and thus both maintaining and exploiting this input sparsity. The resulting differences can be visualized by looking at the pseudo-images from each stage of the feature pyramid. The dense backbone completely destroys all sparsity, while our backbone's use of sub-M convolutions allows this sparsity to be preserved throughout the network. These different backbones can be analyzed theoretically to provide bounds on the number of convolutions performed by both PointPillars and Sparse PointPillars. PointPillars conv count is strictly a function of the width and height of the pseudo-image, as it convolves everything in the pseudo-image, whereas Sparse PointPillars conv count is also a function of pseudo-image density. For the purposes of providing an upper bound, we assume the worst-case placement of structure in a regular grid. We show that, using the median density for our two experimental datasets Kitty and Matterport Chair, Sparse PointPillars performs at least 50% and 79% fewer convolutions respectively. These results also directly translate to theoretical memory consumption. A sparse representation that requires only a fraction of the convolutions also only requires a fraction of the memory. And as we discuss in the next section, memory allocation can play a major role in the empirical performance of these networks on embedded systems. A new pipeline and theoretical analysis is nice, but do these changes actually get better performance in practice? To answer this question, we compare Sparse PointPillars versus PointPillars on two datasets. The first dataset, Matterport Chair, is a custom chair detection dataset derived from Matterport 3D, a dataset of real indoor home scans, with the goal of producing a realistic detection task for a service robot. We run these evaluations on a high-end desktop, on the high power and low power modes of the Jetson Xavier, a popular embedded ML accelerator, and on the CPU of a fetch freight robot base. The second dataset, Kitty, is a famous self-driving car dataset used in the original PointPillars paper, with the goal of characterizing sparse PointPillars versus PointPillars on a popular AV detection task using high-end desktops. We also construct three ablative versions of our Sparse PointPillars pipeline to understand the impact of the sparse operations on our pipeline. On the Matterport Chair detection task, Sparse PointPillars runs faster than PointPillars by a factor of 1.5x on desktop, 1.8x on Xavier's high power setting, almost 3x on Xavier's low power setting, and more than 4x on the robot CPU, all at the cost of about 4 to 6% AP. As an example of the value provided to practitioners, Sparse PointPillars on Xavier's 10-watt 2-core power setting is actually faster than PointPillars on Xavier's 30-watt 8-core mode, allowing practitioners to reduce latency and reduce power consumption by a factor of 3x, all by switching from PointPillars to Sparse PointPillars. This is a huge win worth the trade-off of a slightly lower AP performance for many applications. Here's a puzzle. If you look closely, our sparse backbone is supposed to be faster, but it records significantly slower forward times on all GPU-based accelerators. But bounding box extract times are significantly faster, despite using identical code. Strange. The root cause is actually memory allocation patterns. The sparse matrix allocations are cleaned up during the backbone stage, making the later bounding box memory allocations take significantly less time. Note that the robot CPU has a different memory architecture than GPUs and does not suffer from the same memory allocation issues. This goes to show that sparse pipelines have obvious runtime wins through fewer operations, but they can also have non-obvious runtime wins through better systems pipelining. For Kitty, due to the smaller and more dense pseudo-image, Sparse PointPillars is only slightly faster than PointPillars, but again pays a 4 to 6% BEVAP penalty. These similar performance deltas raise the question: is the performance drop caused by a lack of smearing in our backbone? This motivates 3 ablative models, 2 of which replace later sub-M convolutions with dense convolutions, and 1 which replaced the step-down conv with a wider conv to be able to reach adjacent pseudo-image pixels that were reachable via smearing. These models all show similar or worse performance drops, indicating that sparse pipelines in general are slightly harder to train. Altogether, these results demonstrate that Sparse PointPillars provides a new tool in the practitioner's toolbox for tuning their perception pipeline. A link to our paper, along with the full release of all code, dataset, and model weights are available on our project page, vetter.io/sparsepointpillars.